Okay, all right. So we will talk about properties of Markov chains today, and it's week 5 Wednesday. All right, so we will look. So the first thing I want to talk about is limiting distributions. Okay, and so what is a limiting distribution? All right. So let's just start off. Let's say we've got this two-state Markov chain, state space 0 and 1, and it's got this transition matrix. And so this is what kind of the transition diagram would look like, right? So from 0, we can go back to 0 with probability 0.8. And from 0, we can go to state 1 with probability 0.2. And if we're at state 1, we go back to state 0 with probability 0.6, or we stay at state 1 with probability 0.4. So this is kind of the diagram. And what we kind of want to see is just what happens if you let this chain run for a long time. Okay, so I'm going to start off at state 0, and I'm going to just let it run for a long time. And here I put 1,000, but I think it's in like 100,000. Okay, now I found this website, this cool website. And in here, you can put in a matrix up here. This is a NumPy notation, but you put in a matrix here, and I think you can actually kind of move this around like this. All right, and here, let me crank up the speed. And you can see, okay, so 80% of the time, I mean, it goes from A and it stays back in A, but then, you know, sometimes it'll go to B and sometimes it'll cycle around in B. How many times do we end up in A? How many times do we end up in B? And we can kind of, you know, count this out. And that's what we want to do. We can zoom in a little bit here. Okay. All right, so we're going to let this run for a long time. All right, and I'm going to do it on the computer here. And so this is what I have. I've got P. This is my transition probability matrix, and the first row is 0.8, 0.2, and the next row is 0.6, 0.4. I'm going to let this run for 100,000 iterations, and we're going to start at state 0. So X is going to be 0, and then I've got a whole bunch of NAs that come after that. All right, and so this is how I'm going to just run the chain. I'm going to just run this kind of one at a time. And what we do is we're going to take the previous state. So we're going to start with I for kind of in 2 through N. So I'm going to look at I minus 1, the previous state. And we're going to say, what was X? What was X at time I minus 1? Okay. And then so if X is 0, then we want to select the first row. So we're going to do the row that we select is going to be 0 plus 1. And if the previous state, X is equal to 1, then we want to use the second row in this probability matrix. So the row we select is going to be, you know, this value, which is 1 plus 1, which will be 2. And then, and so to generate the next state, I'm going to just randomly select a value, either 0 or 1. We're either going to pick 0 or 1, and the probability of selecting 0 or 1 is going to be determined by whichever row we have selected, either the first row in the P matrix or the second row in the P matrix. Okay, so the probability is going to be P, whichever row was designated here. And we're going to just select one value, and that's going to be the next value of X at position I here. Okay, is that all right as far as running the chain goes? Okay, so I'm going to just let this run 100,000 times, and then we're going to say, okay, how many times did we end up in state 0? So after 100,000 iterations, the proportion of times I ended up in state 0, I'm going to say, okay, how many times was I in state 0 divided by n? I guess I could have just done mean of X equals 0. So that happened close to 75% of the time, just a little under that, okay? And then here, you know, what was the proportion I ended up in state 1? Around 25% of the time. All right, so I'm gonna try this again. This time we're gonna try a different starting state. So this time my initial state is gonna be 1. Okay, I'm gonna also just change the seed. Initial state 1, we change the seed, and then we just let it run. Okay, same algorithm. And then we say, okay, how many times where are we at state 0? Okay, again, around 75%. Okay, with rounding, we would end up at 75%, a little under here. And then what proportion was I at state 1? You know, basically 1 minus this, so around 25%. Okay, so this is kind of showing us that, you know, if I let this thing run for a really long time, it looks like we're going to end up in state 0 around 75% of the time, and state 1 around 25% of the time. Okay, and you know, if you look at this and you count how many times you get A versus B, you know, we're not getting like it's not streaming out the answers, but you know, we're probably going to get something around well, according to our simulation here, it'll come out around 75% A and 25% B. And so what we find is that both simulations end up approximately 75% of the time in state 0, around 25% of the time in state 1. And we're going to say pi sub 0, we're going to just kind of define some terms and symbols here. We're going to say pi sub 0 is going to be the long run relative frequency that the chain spends at state 0. And pi sub 1 is going to be the long run relative frequency that the chain spends at state 1. Okay, and so we're going to create this vector, this row vector pi, which is going to consist of pi 0 and pi 1, and that's going to be a distribution over the state space 0 and 1, right? So our Markov chain can either produce values of 0 or 1, and this is going to tell us what is the probability that it's at 0 and what's the probability that it's at 1 in the long run relative frequency. And so, you know, from our simulations, we might guess that pi is something around 75% and 25%. Okay, just that's what it appears to be from kind of my two simulations. And if you were to run this more times on your own computer, you'd probably get the same results as I did, or something similar at least, not the exact same results. All right, and so this gives rise to the notion of a limiting distribution, which is going to be the fraction of the time that we spend at state j is going to be pi sub j, right? So same website, you can actually make more complicated Markov chains. So here I've created a 4x4 matrix. If I add a third row here, okay, so now I've got a 3x3 matrix, and so I have a Markov chain with 3 possible states. Okay, and so here's a Markov chain with 4 possible states and stuff like that, and then so you'd have, you know, pi sub state 1, state 2, state 3, or whatever it is. Okay, so whatever values your state can take on, 0, 1, 2, 0, 1, 2, 3, 4. Whatever it is, you're going to have a pi sub whatever state you have, okay? And so if we got pi sub 0, if that equals 0.75, then that means in the long run, the Markov chain is in state 0 around 75% of the time, okay? And so, you know, kind of a little bit more of a definition of what this pi sub j represents. Oh, I'm sorry, instead of zeros, I should put a j here. It's going to be the probability that x of n is in a particular state j, okay, regardless. Oh, so here, if I've got probability that xn is equal to 0, given that I started at state 0, that's going to just be pi 0, and that's 0.75, okay? And it needs to equal the same thing, even if my initial state, x at time 0, was state 1, okay? So whether my state at time 0 was 0 or my state at time 0 was 1, the limit as n goes to infinity needs to be the same, okay? And that's going to be kind of the idea of the limiting distribution, that as n goes to infinity, whether I started off at state 0 or state 1, the probability of being at state 0 is going to be pi sub 0, which is 0.75. Okay, so that the distribution is independent of the initial state x at time 0. Okay. I can't remember. I haven't given you any quiz answers yet. Okay, so let me give you your first quiz answer. First quiz answer is B. B as in boy. B as in boy. Okay. All right, so we're going to define the limiting distribution. We're going to say pi is a limiting distribution. So if we have pi equal to basically a probability distribution over the state space, so if you've got a state space going 0, 1, 2, all the way up to n, we're going to have pi being, pi 0, pi 1, pi 2, up through pi n. Also, maybe I can add this, is that the sum of the pi's have to add up to 1, right? Because it's going to be a probability distribution. So we're going to say pi is a probability distribution, and it's a limiting distribution of the Markov chain where you've got, x at time 0, x at time 1, x at time 2, and so on and so forth. If the probability at x at time n equal to j is equal to pi sub j, regardless of what the initial state was. So x at time 0 could be any value I, where I is any of the initial states, and the probability that x at time n is at state j is going to be pi sub j, okay? So basically, the probability of x being at state j is going to be pi sub j no matter where we started, okay? So it's got to be independent of the initial state for it to be a limiting distribution. If it says, like, if you start over here and the probability that you end up over here is going to at state j is different than if you started over here, then that's not a limiting distribution, right? So if where you started could influence the probability of where you end up, then that's not a limiting distribution. But if where you end up doesn't depend on where you started, x at time 0, then and if that's the case, then you've got a limiting distribution. So if the limiting distribution exists, then this number pi sub j, what that represents is it's going to represent the probability that x at time n is in state j, independent of the initial state x at time 0. And it's also going to be the long run expected fraction of time that the Markov chain spends in state j. So it's going to just kind of be in the long run, how often, what fraction of time does the Markov chain spend in state j? That's what this pi sub j represents. Okay. All right, and then there's another idea here, the stationary distribution. The stationary distribution is another distribution over states such that the expected distribution of the Markov chain at the next time is the same, okay? Meaning this is the stationary distribution of the system at equilibrium. So if you are, if your system is currently distributed according to the stationary distribution, then that means at the next iteration, we would also expect it to be at the stationary distribution. So if there's no change from kind of your current expected state and the next expected state, then you're at the stationary distribution. If you are expecting a change, right? If you've got more in, kind of one state than the other, and you're expecting it to kind of switch at the next iteration, you have not reached the stationary distribution, okay? The stationary distribution is where you've reached some kind of level of equilibrium so that whatever transfers from this state to this state is going to be the same that transfers from this state over back to this state, okay? That you kind of have the same going from one side to the other as going the other way, okay? And so this is an important concept, and there's a theorem that says, if the limiting distribution of the Markov chain exists, it will be the stationary distribution. And so how do we know if the limiting distribution exists? Okay, and we're going to say if a Markov chain is ergodic, it will eventually converge to a stationary distribution, okay? Now you can spend a whole lot of time, you can take a course on stochastic processes and get really into ergodic theory and stuff like this, and you can go down this big kind of rabbit hole. If you just look up ergodic theory on Wikipedia, the article is very long and complex and very mathy, and it's not easy. And there's, if you look at kind of related topics, there's the ergodic hypothesis and an ergodic process, and okay, so anyway, there's a lot, okay? So what I'm gonna just give you some informal definitions that will just kind of give you the gist of some of these big ideas, okay? Without getting into the formal complex math where, you know, if you do decide to study, go to graduate school and stuff, and you take a course on stochastic processes, you'll probably get a lot more into the theoretical math here. But right now, we're just going to give you some informal definitions that will hopefully just at least give you the idea and the gist of these concepts here. Okay, so we're going to say a Markov chain is said to be ergodic if we can start the state at we can start the chain at any state I, right? So whatever your state space is, you've got a whole bunch of different states that it can be in. You can start the chain anywhere at state I, and that at some point in the future, okay? It could be in the distant future, but at some point, we can't just say infinitely into the future, okay? But at some point in the future, there's going to be some time t, right? At some time t in the future, the probability of being in any of the other states that exist in the Markov chain, that all of them have a probability greater than 0. Okay, so if you can start at any state and have a non-zero probability to end up at all of the other states, any of the other states, then it's going to be ergodic, right? But if it says, like, if you start at this state, you know, and that means this one state in the future is like impossible, then it's not going to be ergodic, right? If there's no possibility of you reaching a particular state in the future, then that's not going to be an ergodic chain. But if every single state has a non-zero probability at some point in the future, then it'll be ergodic, okay? And so this has to be true for basically all t greater than some finite integer t0, okay? So you just kind of say, well, you know, at least after the, you know, 10,000th iteration, this will be true, okay? And so for a Markov chain to be ergodic, it's got to be irreducible and aperiodic. And I will define, well, not define, I will give you informal definitions for irreducible and aperiodic here, okay? So it has to be irreducible and aperiodic. And they kind of line up with what it means to be ergodic. Okay, so a Markov chain is irreducible if all the states communicate with each other, okay? And if it's not irreducible, then we say it's a reducible Markov chain, okay? And so we'll say two states I and j communicate with each other if there's a path to go from I to j and there's a path to go from j to I, okay? And that path doesn't have to be a direct path. It can go through other states. So if you look at this Markov chain diagram, all of the states communicate with each other, right? So if you start at state 0, can you get to state 3? Yes, you have to go through states 1 and 2, but you can get to state 3. You can go from 0 through here, and end up at state 3. Does state 3 communicate to 0? Yes, you can start at state 3, and you can go through 2, 1, and end up at 0, okay? So states 0 and 3 communicate. And if you look at any other pairs of states, all of the states communicate with each other. You can say, well, does 0 communicate with 1? Yes. 2, 3, and 4? Yes. Does 1 communicate with 0, 2, 3, and 4? Yes. And all of the states communicate to each other. And so if you start at any of these states, there will be a path to any of the other states. Okay, so this chain, this Markov chain is irreducible. Okay, this is a reducible chain, okay? All the states do not communicate with each other, right? So if you start at state 0, 1, or 2, there's no path that will get you to state 3 or 4, right? So if you start at 0, can you get to state 3? No, there's no way to get to state 3, okay? And if you start at 1 or 2, there's no way also for you to get to state 3. Okay, so 0 does not communicate with 3. 3 has, we might say 3 has access to 0, but 0 has no access to 3. So 0 and 3 don't communicate. And we might say, so we will say this is reducible because technically, if a chain starts off in state 0, 1, and 2, you can reduce this diagram to just be these 3 states, 0, 1, and 2. There's no point in keeping basically states 3 and 4 in your diagram if you start your Markov chain at 0, 1, and 2. Okay, so this would be a reducible chain. All right, is that okay for this concept of irreducible? Okay, the period of a state is a little bit more complex, okay? And so the period of the state is the greatest common divisor, divisor of n, which is the number of states you can take and end up back at kind of the state where you started. So let's look at state 3, right? And we're going to say, what is the period of state 3? Okay, so we can say, well, how can I start at state 3 and end up back at state 3? Okay, so I can go from 3 to 2 back to 3, and that's 2 steps. Okay, 3 to 2 is 1, and from 2 to 3 is a second step. So I can do 1, 2. So I can end up back at 3 in 2 steps. Okay, I can also go from 3 to 4 back, and I can do this, right? 1, 2, 3, 4. Okay, and you're allowed to kind of visit yourself before that. That's allowed. Okay, so that would be 4 steps, right? This is 1 step, 2 steps, 3 steps, 4 steps. Okay, I mean, I could also go this way, 1, 2, 3, 4, and I can also go this way, and I could go 1, 2, 3, 4, 5, 6, right? So I can go 3, 2, 1, 0, 1, 2, 3. That's 6 steps, and you can kind of play around with it and try to say, well, how many different ways can I get back? And what you're going to find is that they're all going to be an even number of steps. Okay, there's no way to end up back at 3 in an odd number of steps. If you start at 3, you can't get back at 3 in an odd number of steps. So the greatest common divisor of kind of all of the steps you can take, 2, 4, 6, 8, so on and so forth, you've got a greatest common divisor of 2. And so state 3 has a period of 2. Okay, and if you look at any of the other states, all of the states have a period of 2. Does that kind of make sense for this diagram? So we've got a period of 2. Okay, if so this diagram is the same, except I've added 1 path here where 4 can go back to itself. Okay, and so if we look at this, and let's look at state 3 again, and we say, well, how many steps can I take to end up back at 3? Okay, I can go from 3 to 4 back to 3, and that's 2 steps. But I can also go 3 to 4, and from 4 back to 4, back to 3, and that would be 3 steps. Okay, so I can go 1, 2, 3. Okay, and I can also go 1, 2, 3, 4, right? I can visit 4 twice. I can visit 4 3 times before going back. Okay, and I can also kind of follow any of these other things. And so if we look at the number of steps it takes to get back to 3, there's lots of options, and I can take 2, 3, 4, 5, 6, 7, 8, basically any whole number of steps greater than 2. And so state 3, the greatest common divisor of all of these numbers is just going to be 1. And so state 3 has a period of 1. Okay, and so, you know, anytime you have a state that goes back to itself, you can kind of abuse the idea of just visiting it over and over and over again. And you can see that all of the states, you know, will have a period of 1. Okay. What's the difference between minimum steps it takes to start at J and end at J versus the state periods? So it's not the minimum number of steps, okay? Because the minimum number of steps to start at 3 and end up back at 3 is 2, right? You have to either go to 2 and then back to 3. That's going to be, so the minimum number of steps is 2 for 3, but that's not what we're asking, okay? We're asking, like, are we restricted? So over here, we're restricted to ending up back at state 3 basically on the even beats, right? So we can only end up back at state 3 at state 2, or after 2 steps, 4 steps, 6 steps, 8 steps, okay? Over here, because I've got kind of this little loop over here, I can end up back at state 3 on the 2nd step, 3rd step, 4th step, or 5th step, or 6th step. So it's not the minimum number of steps, but it's kind of, is there a certain period and certain interval at which we can end up back at ourselves, back at the starting state, okay? And so for this case, it's not, okay? So it's not the minimum number of steps, so it's like, does it happen only at certain intervals? Here, you can only end up back at the self on every 2nd step, okay, on even beats, okay? And so here I can actually show you an example. So if I let me do 0, 1.0, and so if I okay, so here, this is a Markov chain, okay? This is a Markov chain with a period, each of these states have a period of 3, right? How many steps does it take to get back to A? Okay, in this case, it's gonna happen either, you have to go 1, 2, 3, 3, 6, 9, 12. Those are the, that's how you can end up back at A, right? You can't, there's no other, you can't get back to state A in 2 steps or 4 steps or 5 steps, okay? It's either gonna be 3 steps, 6 steps, or 9 steps, and things like that, okay? So this will have a period of 3. Okay, but then if I change one of these, if I just make it possible to go back to one of the states, okay, all right. So just the fact that I've added this thing where from state A, we can end up back at state A. Now, how many steps does it take to get back to state A? Or even, let's say, from B back to state B, then it can happen, you can take 1, 2, 3 steps, but you can also go 1, 2, and then spend a loop there and get back in 3, 4 steps. And you can loop around A a couple more times and take 5, 6, 7, 8, 9, or 10 steps, right? So as soon as I've added this possibility of looping back to A, then we're not restricted by multiples of 3 anymore. Is that okay? All right, and so overall, we would say a Markov chain is aperiodic if all the states have a period of 1, okay? And a Markov chain, if a Markov chain is irreducible, and if one of the states can go back to itself, then the chain will be aperiodic. This is not the only condition, this is not the only way for something to be aperiodic. So for example, I can get rid of this thing where it goes back to itself, but this will also be an aperiodic chain, okay? So we can say, how many steps does it take to get back to A? And we can take 1, 2, or we can take 1, 2, 3, or we can take 1, 2, 3, 4, or 1, 2, 3, 1, 2, 3, 4, 5, right? So we can kind of take any kind of combination of going to C or B, and this will also be aperiodic, okay? So we don't have any state that goes back to itself, but this is also an aperiodic Markov chain because you can go from anything, these things, not at some kind of interval. You can end up back itself at kind of the second, third, fourth, fifth, or whatever beat you have. Okay, so that's aperiodic chains. And so we're saying if it's irreducible and aperiodic, then eventually we're going to reach some kind of limiting or stationary distribution. Let me go ahead and give you your second quiz answer. Second quiz answer is D. D as in dog. D as in dog. Second quiz answer. Okay, so so this is let's revisit our two-state Markov chain. Okay, and this is what we have. We got 0.8, 0.2, and 0.6, 0.4. So this is what we have. All right, and so this is ergodic, and it's irreducible. It's aperiodic. Okay, which means it's ergodic, and this means that there is some limiting distribution. And we kind of saw that just empirically when we ran the Markov chain for a long time. And what we want to do is we kind of want to find when we will have equilibrium, right? And so we'll have equilibrium when the amount going from 0 to 1 is equal to the amount flowing from 1 to 0. Okay, so if you think of these as kind of like, you know, I don't know, something. All right, so you'll achieve equilibrium when the amount going this way is equal to the amount going this way. All right. So what's the probability of transitioning from state 0 to state 1 and transitioning from state 1 to state 0? That's when we'll have equilibrium. So if you're already at state 0, the probability of going to state 1 is 0.2. Okay. And so the total probability of transitioning from state 0 to state 1 is going to be the probability of starting at state 0 or being at state 0 multiplied by the probability of transitioning from state 0 to state 1. Okay, so I'm going to just say probability of being at state 0 is P0 multiplied by the transition probability, which is P01. Okay, and then also if you're already at state 1, the probability of going to state 0 is 0.6, P10. That's, again, these are just values in the P matrix. P10 is 0.6, and the probability, yeah, that's probability of going from 1 to 0 if you're already at 1. And so the total probability of transitioning from state 1 to state 0 is going to be the probability of being at state 1 multiplied by that transition probability. And so we'll do P1 times P10. Okay. And what we want to do is we want to set this equal, these two things equal to each other. Okay. We want the amount going from over here to here and the amount coming from over here to here to be equal to each other. And that's when we'll have equilibrium, right? So that we're not having the amount going from one side to the other is the, okay, and that way we're not going to get like a population change where one side's going to grow and the other side's going to shrink. If the amount going from one side to the other is equal, then we'll achieve equilibrium. So we want to find values pi 0 and pi 1 that satisfy pi 0 times P01. So I'm just replacing, so I'm going to set this equal to this, but I'm going to say we're going to call this pi 0 and pi 1 because that's what we will have at equilibrium. Okay, so we've got pi 0 times P01 is equal to pi 1 times P10. All right, so P01 is the value in that top right corner, which is 0.2. So I've got 0.2 times pi 0. And this is 0.6, and I got 0.6 times pi 1. We're going to set these two equal to each other. And then there's a constraint that pi 0 and pi 1 have to add up to 1 because they are part of a distribution. So they're going to add up to 1. All right, and so when you solve, if you solve this and this, these kind of the system of two equations, all right, you find that pi 0 over pi 1 is going to be 3. And the, you know, what satisfies that is going to be pi 0 is 0.75 and pi 1 is 0.25, which matches what we found when we did kind of the Markov chain when we ran it ourselves. Okay, we got pi 0 is 0.75 and pi 1 equal to 0.25. Okay, and this will be our stationary distribution. Okay, so if I say my stationary distribution pi is equal to 0.75, 0.25, we can see that if this is my distribution at whatever time it is, and I multiply it by the transition matrix P, we're going to get back pi. We're going to get pi back. Okay, so if I do 0.75 times 0.25 and I multiply it by this matrix, the transition probability matrix, okay, 0.75 times 0.8 is 0.6, 0.25 times 0.6, so just doing matrix multiplication, we're going to get 0.15. Okay, second column, 0.75 times 0.2 is 0.15, and 0.25 times 0.4 is 0.1, okay? And so we also get back, so when I do this, 0.6 and 0.15, that adds up to 0.75, and 0.15 and 0.1 adds up to 0.25. So all this is saying is that when you take your stationary distribution and you apply the transition matrix, you get the stationary distribution back, right? So nothing has changed. Once you've achieved the stationary distribution and you multiply by the transition matrix, the distribution doesn't change. This is why we call it the stationary distribution, is that at this point, the distribution remains stationary. It's not in flux. Everything's at equilibrium. The amount going from one state to another equals the amount going back to it. So everything's gonna stay steady here. Okay, so the stationary distribution satisfies this property, right? So we've got this row vector pi. So we've got pi times the matrix P is equal to pi. Okay, so I've got a vector times a matrix is equal to just the vector itself. Okay, and so this is what we call the left eigenvector of the matrix P, the left eigenvector. Okay, so normally when you take linear algebra and stuff, when you talk about eigenvectors, we generally talk about the right eigenvector. The right eigenvector is in the setup where you have a matrix times a vector is equal to a constant times the vector, okay? And in our case, our lambda, our eigenvalue is a 1 here, okay? And it's a right eigenvector because the vector is on the right side of the matrix. You have the matrix times the vector. But here I've got the vector on the left side of the matrix, okay? And so this is known as the left eigenvector, okay? All right, well, the left eigenvector is equivalent to basically the transpose of the right eigenvector of the transpose of the matrix, right? So if I take this and I take the transpose, okay, I've got P transpose times basically a vector, and it equals that vector, okay? And so pi is just the transpose of the right eigenvector of P transpose, okay? So the left eigenvector, which is a row vector, is equal to the transpose of the right eigenvector of P transpose. Okay, so it's a little weird, but they're similar. Okay, so here I can just do this with a little bit of math here, or using the computer. So when you use the function eigen in R, it's going to find the right eigenvectors. So what we want is we want the left eigenvectors. Okay, so here's my transition matrix P, 0.8, 0.2, 0.6, 0.4. And I want the left eigenvectors. So what I'm going to do is I'm going to take the transpose of P, and I'm going to get the right eigenvectors of the transpose of P. Okay, I get the right eigenvectors of P transpose. And then we look at this first column. Okay, we look at this first column, and this is the values in the first column are positive, and so those are the values we're going to use. Okay, we can't use the second column because we've got positive and negative values. So that's not going to work for probability distribution. Probability distributions, you can't have any negative values. So we take these positive values, and the left eigenvector is a row vector. So I'm going to just transpose this first column here. I'm going to take this first column and transpose it. And then I'm going to normalize it. So I'm going to take the sum of this column and I'm going to divide it by the sum. And that way it adds up to 1. And so I get the left eigenvector of P is 0.75, 0.25, okay? And that matches kind of our calculations for finding the stationary distribution. And that makes sense because, you know, this will satisfy the condition that if I take this and I multiply it by this, I'm going to get back the same row vector there. Okay, is that all right? Is that working out okay? All right, let me give you the last quiz answer. I've got a couple more things I want to show you that I'm excited for. Okay, so the last quiz answer for today is A as an apple. A as an apple is the last quiz answer. A as an apple. Okay, so here's I've got some visualization here. Okay, so here we have the probability of transitioning from. So here is this website, explain visually, and we can kind of program in the transition probability. So we're going to call California state 0 and New York will be state 1. And we'll say the transition probability of going from California to New York is 0.2. And the transition probability of going from New York to California is going to be 0.6. Okay, so I've kind of done this. And you know, on this thing, you can actually adjust kind of the transition probabilities. Okay, but here it was kind of tricky because you have to use your mouse. So I finally got it to be 0.2 and 0.6. Okay. And what we can see is I can start off the population of California to be huge or small, and it doesn't matter, okay? No matter how I start this thing off, eventually it'll reach this system of equilibrium here, okay? So I can start off with New York having a huge population and California having a small population, but as long as we have this Q is 0.2 and P is 0.6, eventually we're going to reach the stationary distribution where California is going to have 75% of the population and New York will have 25%. Okay, so just watch what happens. Okay, so we start off with so many people at New York, okay, but we're going to move 60% of New Yorkers to California, and at each step, 25% of Californians will move to New York. Okay, so let me just kind of reset this. Okay, so this is where we start. 60% of New York will move to California, 20%. Okay, 60% of New York will move to California, 20% of California will move to New York. Okay, so that's what we're going to see. All right, and then we just kind of keep running this, and eventually we reach a state of equilibrium where the amount flowing from New York to California is equal to the amount flowing from California to New York. Okay, so I can start off with something. I can start off the other way. I can start with California being huge and New York being tiny. Okay, so I got no one living in New York right now. Okay, and we're going to move 25% of California to New York, or 20%, and then 60% of New York to California, and 20% go this way, and 60% comes back this way, and 20% goes this way. And now we've reached equilibrium where the amount flowing from this way over here is equal to the amount flowing from that way over there. Okay. Let's see. All right, so right here, it's very easy. Here you can see 2 goes that way and 2 come back this way. All right, so I mean approximately so, right? So we've got about, let's see what will add up. So if I do four and let's see how this flows. Okay, so if we do this, we've got 5 going this way and 5 dots coming this way, right? So we've achieved equilibrium. So this is kind of what you have, and you can kind of mess around with this. And so here I'm going to just kind of say 90% and 0.08 or something. All right. So what happens? So this is saying like almost 90% of Californians will go to New York and only 8%. Okay. So no matter where I start, eventually we will reach a state of equilibrium where the amount going from California to New York is equal to the amount flowing from New York to California, okay? And you can kind of change these proportions, okay? And still, eventually you will reach a point of equilibrium where kind of the size of the circles remain the same, that the amount going from one way to the other and flowing back is equal to the same. And it doesn't matter where you start. Okay, you can start with a huge California and a small New York, and eventually it will converge. And so what's being plotted over here is just kind of the initial population sizes, where California is huge and New York is tiny. And what happens is they plot the size of California and the size of New York, and eventually it's going to reach this spot, this vector, which represents the eigenvector of kind of this transition probability matrix, which is pretty, so anyway, I thought this is kind of a neat visualization of reaching equilibrium. Okay, anyway, you should play around with it. I thought it was cool. I don't know, maybe you guys think it's cool or not, but okay, so this is where we are headed next, okay? So what I tried to show you today was that if you've got a Markov chain that's ergodic, an ergodic Markov chain, and it's got some transition probability matrix P, then it's got a stationary distribution pi, okay? And we can figure that out. We take the, you know, the left eigenvector of P. And when you have that stationary distribution, what that means is that if you let the Markov chain run long enough, then it will converge to the stationary distribution. And once it converges to the stationary distribution, then all of the values that it's going to generate will come from the stationary distribution, right? Once it reaches that stationary distribution, it's going to stay at the stationary distribution. And all of the random values that it generates comes from that stationary distribution. So this is what we want to do next, okay? Let's say there's some target probability distribution that we want to be able to generate values from, okay? Can we design a Markov chain, okay? And when we talk about designing a Markov chain, that means, can we figure out the transition probabilities so that the stationary distribution of this Markov chain that we're designing, can we make it so that that stationary distribution is equal to the desired target distribution? Because if we can achieve that, then we can just start the Markov chain anywhere, let it run for a long time, let it reach its stationary distribution, and then once it reaches the stationary distribution, it will just keep generating random values from that stationary distribution, which is the distribution that we want, okay? So that's what we want to do. We want to figure out what kind of transition probabilities to use for this new Markov chain, and we want to pick the transition probabilities in such a way that its stationary distribution is equal to the target probability distribution that we want, okay? And so that's where we're headed next. That's going to be the Metropolis algorithm and the Metropolis-Hastings algorithm. Yeah, and it's pretty exciting, I think. I don't know. I get excited over stuff like this. So, so that's all I've got for you guys today. So we'll end here, and we'll see you guys on Friday. And yeah, I hope you guys are all doing well. So, so we'll end here.